In this presentation, we'll take a look at thermal interactions, thermal interference between borehole heat exchanger systems. We'll give a short introduction and then we'll start talking about methods to assess the thermal interference, how to account for the thermal interference in design, and how we can optimize large-scale ground heat exchanger fields. So basically, what is thermal interference? In the graphics below, you can see three calculations of borehole heat exchangers with exactly the same energy extraction profile. And you can see that as we have more heat exchangers in the same area, that the temperature in the center will be lower than when we only have one heat exchanger. And this is different in collective systems where they are hydraulically coupled and the temperatures even out, but the heat extraction rate is less for a heat exchanger in the center than for a heat exchanger at the edge. But in individual systems that we often have in practice, the actual temperatures of the systems depend on the relative location. So, definitions of thermal interference. First of all, we talk about thermal interactions. These are temperature effects between the borehole heat exchangers or shallow geothermal systems that are hydraulically coupled into one system. So what we call a collective system. The design software that we have available will deal with this and let's say calculate the relative contribution of the individual heat exchangers from the point of energy to the whole. Then thermal interference. These are temperature effects between shallow geothermal systems, borehole heat exchangers, that are not hydraulically coupled. So these are individual systems, each with their own design, their own depth, their own number of heat exchangers, and also their own energy profile. They can be different between all the systems. Now, if we do not account for these temperature effects, then we have negative thermal interference. We have a temperature effect that is not accounted for during design and that will lower or heighten, will decrease or increase the temperature with regard to the design goal that I had in mind as a designer. So it may have a negative impact on the design efficiency. I make reference here to the deliverable 3.1 of the GeoBoost project, the framework for technical and legal assessment of thermal interference and optimized planning of open and closed loop systems, which covers a lot of these aspects and also goes into detail about the different methodologies in different countries. I will look mainly at the methodology as we have developed it in the Netherlands, and that is based first of all on, let's say, the principle of heat transfer around the borehole heat exchanger that we already discussed in module 1.2. The basic idea here is that the further we move away from a particular borehole heat exchanger, the smaller the temperature change in the ground will be. If we then look at several heat exchangers in the ground in each other's vicinity, then the basic principle is superposition. We need to add all the individual temperature effects of the individual heat exchangers together to get the total temperature profile in the ground. And for individual heat exchangers, we do exactly this. We add up the individual effects and we see a lowering of temperature. In design methodologies like Earth Energy Designer or GLIPRO or EWS, different codes exist. Usually the average over the whole borehole field is calculated and the effects of interactions are expressed as more or less heat extraction from a particular borehole, depending on the situation, on the relative position in the borehole field. So, negative thermal interference, temperature effects not accounted for during design and affecting efficiency. With collective systems, you have a pooled energy demand profile. So if you have 5 different houses with 5 different energy profiles, you add them all up together and you treat it as one heat pump system. The effect between individual boreholes is accounted for, but we get average fluid temperatures. In fact, when we have multiple individual systems, we have different energy demand profiles. We have several heat pump systems with maybe different heat pumps and different capacities. We have different heat boreholes with different depths, and the effects between the individual systems cannot be accounted for. Individual temperatures individual temperature effects need to be calculated. There are several ways in which we can do this, and we find in literature different strategies to exist with these type of thermal interferences. For instance, a design-based procedure or ad hoc distance between systems. Let's put them 20 meters apart or 30 meters apart, and then we expect no interaction. Or we define a temperature effect on the partial boundary. For planning purposes, some countries provide an online tool to assist in the planning, usually based on some assumptions about energy demand profiles and design methodology. In the Netherlands, and the little icon on the right shows you the SIKB, which is the Dutch protocol holder. In the Netherlands, we have a formal procedure for assessing the thermal interference between systems, which has been required by law and in effect since 2013. This objective method, which is based on the finite line source solution, is freely available as an Excel tool, but for more complex situations, commercial tools are also available.